Our research question was to determine whether the mass of a falling object affected the resistive forces acting upon it. In order to test this, we wanted to do it in a controlled manner by isolating the mass as the independent variable in order to gain a better understanding of drag and other resistive forces. The main physics principles we used were force, specifically drag force, as the formula shows below, the conservation of energy, as the energy does not change due to the conservation of energy, it is only transferred within the system, and then Newton's second law. The only variable that was changed in our experiment was mass. In order for there to be fewer extraneous variables, we kept this variable isolated, although there was minimal change to the surface area with the addition of each plate. The way they fell in each trial did not affect how the surface area contributed to drag or other resistive forces. Ultimately, we were trying to measure how drag affected the change in mass while keeping the density and surface area roughly the same. So this is our system schema, our energy diagram, and our free body diagram. In the free body diagram, you can see that resistive force is not as much as the force of gravity, which is why the object moves in a continual downward motion. However, once it reaches terminal velocity, which it did not specifically in this experiment, the force of drag and the force of gravity would be equal, and the object would not accelerate. In the energy pie charts, you can see that energy is leaving the system as the pie charts get smaller. The first pie chart is at the top of the ladder where the plate has not been dropped yet. Afterwards, the plate has been dropped. It still has gravitational energy as it is above the surface of the Earth, but it's mostly kinetic energy. And when it hits the ground, it has full potential or full kinetic energy. In the system schema, you can tell that the system is largely denoted and isolated to only the paper plate, which is why the energy pie charts get smaller and there's energy quote unquote leaving the system.
For methods, we recorded 3 videos of 3 plates, each with a different mass, falling from the same height. The first plate had a mass of 19.21 grams. The second plate had a mass of 41.02 grams. And the third plate had a mass of 64.77 grams. Then we uploaded the videos into Tracker. We created a calibration using the meter stick as a reference frame, and we tracked each plate while falling in order to measure velocity and force. Finally, we calculated the final velocities of each plate, air resistance, and theoretical terminal velocity. Trial 1 is of the plate with the mass of 19.21 grams, and the overall trend of the velocity versus time graph is linear. The points on the graph itself do not exhibit a linear behavior, though. As you can see, some of the points go up and down, and this can be attributed to the behavior of the falling paper plate. It might not have fallen flat, and when it tilts sideways, it's going to have a faster velocity than if it falls flat. Trial 2 was of the plate with a mass of 41.02 grams. The overall trend of the velocity versus time graph isn't really linear, and this can be explained by the point between 4.45 seconds and 4.55 seconds. There's a big spike, but this can be due to part of the plate touching the ground but not coming to a complete stop in the video, and it just being a tracker and human error. Trial 3 was of the plate with the mass of 64.77 grams, and in the velocity versus time graph, like Trial 1, the overall trend of the velocity versus time graph is linear, but the points on the graph itself do not exhibit a linear behavior. And like in Trial 1, this can be attributed to the behavior of the falling paper plate because it might not necessarily fall flat, and if it tilts sideways, it will have a faster velocity than when it falls flat. And like in Trial 2, there's a small spike between seconds 2.7 and 2.8, and this can be due to the plate partially touching the ground but not coming to complete rest, and this being a tracker and human error.
For our calculations, we started by listing the masses of the plates before calculating the surface area of the plates used, finding the density of air, and estimating the coefficient of drag. This allowed us to calculate the terminal velocity and the force of drag for each mass. The equation for terminal velocity is square root 2 mass times gravity divided by the square root of PACD. The terminal velocities were found to increase as the mass increased. We then calculated the force of drag with the equation 1/2 CD PAV squared. The force of drag also increased as mass increased. Our results show that the larger the mass, the greater the terminal velocity, and therefore the larger the force of drag. These results also follow Newton's second law. Our quantitative data cannot be considered entirely accurate and may be due to human error in creating a point mass on tracker, the shape of the plate affecting the velocity during its descent, and estimating the coefficient of drag. The coefficient of drag used in our calculations is for a short cylinder, so it is not completely accurate and may have affected our calculations. The terminal velocities calculated are smaller than what our graphs show and may be due to this estimation.